The limiting reactant. The coefficients of equations are sometimes called stoichiometric coefficients. So these numbers that we're looking at in front of each one of these compounds, we looked at them, and way back when we first learned about chemical reactions, we knew, well, okay, it meant that we had 2 of these, 1 of these, maybe 5 of those. Okay, but we realized that there's a relationship that we can kind of use in terms of a mole ratio. So how many moles of this to how many moles of that to produce X number of moles of a product. So reactants are said to be present in stoichiometric amounts when they are present in a mole ratio that corresponds exactly to the mole ratio predicted by the balanced chemical equation. This means that when the reaction is complete, there are no reactants left. So what we have is we're using up both, let's say, the nitrogen gas and the hydrogen gas. We're using it up completely, meaning that there's nothing left over, and everything has been put together. But ideally, that would be great to happen, but realistically, that's not what happens. Okay. So, reactions almost never have reactants in stoichiometric amounts. So as I was mentioning before, in terms of cellular respiration, so you have glucose. Okay, so 1 molecule of glucose, okay, to combine with 6 molecules of oxygen to produce 6 molecules of carbon dioxide to 6 molecules of water, which means now, okay, if we look back at the mole ratio, well, we have 1 mole, okay, to 6 moles, okay, to 6 moles. Okay, to 6 moles. Okay, so we can treat it that way as well. Okay, but ideally, but realistically, right, this amount is constantly present. Okay, so as we said, limitless supply of oxygen present, but the amount of glucose is limited to the amount the animal has eaten. So it depends yourself when you're breaking down the glucose in your body. Okay, this reaction is limited to how much glucose you have in your body. Determining the limiting reactant. The reactant that is completely used up in a chemical reaction is called the limiting reactant. When the limiting reactant is used up, the reaction stops. Okay, just like what we talked about with the glucose. Once the glucose is done, regardless, you're going to still have that input of oxygen there, but if there's no glucose there, how can that reaction continue any further? Okay, so a reactant that remains after a reaction is over is called the excess reactant. Okay. So whatever is left over, whatever didn't get a chance to get broken down, okay, is considered in excess. Right? We have more of it. When you're given amounts of 2 or more reactants to solve a stoichiometric problem, you first need to identify the limiting reactant. Okay, find out how much product would be produced by each reactant if the other reactant were present in excess. The reactant that produces the least amount of product is the limiting reactant, as we've talked about just a second ago. Okay, so we're going to look at similar, our stoichiometric problems that we've looked at last class. Okay, but now we're going to actually try to figure out which one is going to run out first, and which one's going to be still left over, okay, with this reaction. So let's look at the first problem, sample problem. Lithium nitride reacts with water to form ammonia and lithium hydroxide. Okay, if 4.87 grams of lithium nitride reacts with 5.80 grams of water, find the limiting reactant. Okay, so we've started off. I've given you here the equation, but you want to make sure that you actually, that's the first thing you want to start off with. Okay? So, what do we have? Well, we look at our question again. So remember, always look through your question once. Then try to extract whatever information you need to extract. Okay? So you put together your equation. So, if 4.87 grams of lithium nitride, so 4.87 grams of lithium nitride is going to react with 5.80 grams of water. Which one, okay, is going to run out first? That's really what you're trying to find out. Which one's going to be still left over when this reaction takes place. Okay? And we can't just look at it as, well, we've got more mass of this than the other. Right? We're also looking at, for every 1 mole of lithium nitride, we need 3 moles of water. Okay? So, first steps first. What I want you guys to do is, if we have mass, what do you think we can find with that? The number of moles. So that's what we know that there's a 1-to-3 ratio, but with how much we have, find the number of moles. Right? Remember, most important piece here is this equation where we're given molar mass, and the number of moles. So we have the mass, we can calculate the molar mass with the periodic table. We want to find the number of moles of each one of those reactants. So take a moment and find those. So the N of lithium nitride. So we start off with our mass, which is 4.87 grams. And we're going to divide it by the molar mass of lithium nitride, which is 34.8 grams per mole. Okay. Grams cancel out, leaving me with 0.140 mole of lithium nitride. Okay. So, then let's try to find the number of moles of water. We know the mass that we're using. We want to find out the number of moles. So now we have 5.85 grams divided by the molar mass of water, which is 18.0 grams per mole. Again, grams cancel out, and we're equal to 0.322 mole of H2O. Okay. So, this is the ratio. Okay, we have 0.140 moles of lithium nitride to 0.322 moles of water. Now, using that information, we can go into our chart, our stoichiometric chart. Okay, so let's put up our table. Okay, so here we're going to list. Now, what we want to do for this is we have the moles, right? Remember last time we were calculating? One of these was what we had to find. Right? So now, where's the unknown? The unknown is you want to figure out how much product you're going to make. So your unknown you're going to make is either that or that. That's going to be your unknown. The one I usually like to pick, I like to pick the one that has 1 in front of it. Okay. So what we're going to do is our unknown. Okay, remember we have mole, and then we have molecules. Okay, our unknown, we're going to put, is going to be the ammonia, NH3. That's going to be our unknown. So we want to find out the number of moles we have of that. But now, for the rest of the table, remember we only used, okay, we only listed 2 things. But now we're actually going to list 3 things. Okay. We are going to list our lithium nitride. And we are going to list our water. So, how many moles do we have of lithium nitride? We just calculated 0.140. How many moles of water have we calculated? 0.322. Now, how many molecules have we created of ammonia? 1. How many moles are we using of lithium nitride? 1. How many moles of water? 3. So now, remember what we said? We use the table, right? We use the table and we separate the mole to molecule to find our ratio of moles, right? But now we have 3 of them. So what do? Well, we treat it as if, let's find this first, right? So we're going to find, okay, the number of moles that we're going to create of ammonia if we're using that many moles of lithium nitride. Then we're going to do the same thing, but now we're going to use the number of moles of water to find out how many moles of ammonia we're going to find. Okay, so take a moment and copy out, and actually solve for the number of moles for ammonia when it's created using lithium nitride and used when creating with water. What we're going to do now is we're going to find the ratio, we're going to compare the ratio of ammonia, okay, to lithium nitride. So we're going to use this. Remember what we said? The separation, we treat it as if they're equal, right? So we're going to have X moles of ammonia, okay, over 0.140 moles, okay, of lithium nitride equals 1 molecule, okay, of ammonia over 1 molecule, okay, of lithium nitride. So what we do, we take this here at the bottom, we bring it up there, and we're left with X is equal to 0.140 times 1 over 1, which will give me the same thing, right? 0.140 moles of what? Of ammonia, right? So, with this many moles of lithium nitride, we're going to make the same amount of moles of the ammonia. So now, what we're going to do is, we're going to find now the ratio of the ammonia to water, doing the same thing. But now we're going to ignore this part, right? We don't need this. We've already used that. So we're going to have X, okay, X moles of ammonia over 0.322 moles of water is equal to 1 molecule of ammonia over 3 molecules of water. And so we're going to bring this over, and we're going to get the number of moles of ammonia, okay, number of moles of ammonia is equal to 0.322 times 1 over 3. And when we multiply them together, what do we get? 0.107 moles of ammonia. So, the lithium nitride makes this much ammonia. The water is going to make this much ammonia. Which is making more? The lithium nitride. Which makes which one the limiting reactant? The water. The water, okay, the water here is the limiting reactant. Because the water is producing less ammonia. Okay. So the water is considered because all of a sudden, well, we have 0.14 moles of ammonia produced as opposed to 0.107 moles of ammonia that is produced by water. Okay? So the limiting reactant is going to be water because it creates less of the product. Now, we could have done this and that using lithium hydroxide if we wanted to. Okay? It really wouldn't have mattered. And we'd still get a greater answer, okay, okay, with the lithium nitride than we would with the water. But we choose only one of our products to kind of make the comparison. Okay. Sample problem. White phosphorus consists of a molecule made up of 4 phosphorus atoms. It burns in pure oxygen to produce tetraphosphorus decoxide. A 1.00 gram piece of phosphorus is burned in a flask filled with 2.60 times 10 to the power of 23 molecules of oxygen gas. What mass, okay, of the tetraphosphorus decoxide is produced? Okay. So we need to figure out from this information, what are we given? Okay. So we are given 1.00 gram piece of phosphorus. Okay. We are also given a flask of 2.60 times 10 to the power of 23 molecules of oxygen gas. So when we're trying to figure out ultimately our limiting reactant, that's going to be our unknown. But we want to convert both of these, okay, both of these into what? Moles. Okay, so we want to convert the mass that we have of phosphorus, the number of molecules that we have for oxygen, into moles. The number of moles, okay, in phosphorus. So we have the mass of phosphorus, right? Because we use the pyramid, right? Molar mass, mass, number of moles. So we're trying to find this. So we're given that, and we can calculate that. So we've got 1.00 grams divided by the molar mass, which is 123.9 grams per mole. Grams cancel out. And I'm left with, and I have to put mine in scientific notation, 8.07 times 10 to the power of negative 3 moles. If you use all the zeros, that's fine. Okay, you can simplify it for yourself if you wish. If not, don't worry about it. So we have this many moles of phosphorus. Now we want to find the number of moles, okay, of oxygen. We know that we have 2.60 times 10 to the power of 23 molecules. We know that 1 mole of oxygen has how many molecules? 6.02 times 10 to the power of 23. Right? So we're going to divide this by 6.02 times 10 to the power of 23 molecules per mole. Molecules cancel out, and I'm left with 0.432 moles of oxygen. Okay. So I have that. Now, we have the number of moles of my reactants. So what we're going to do is, my unknown is going to be one of my products. But we only have one product. So we just list that, right? We put that. So we create our list. Okay. So we have moles and molecules. So, first one we're going to put in here is my unknown, P4O10. We don't know how many moles, but how many molecules in this balance equation? 1. Okay. Now, the next thing we have is the phosphorus. And how many moles do we have of that? Well, we calculated that. 0.07 times 10 power of negative 3 moles. And we have how many molecules in the equation? Only 1. And the last one we have is oxygen. How many moles of oxygen? 0.432 moles. And how many molecules do we have? 5. Okay. So, just like we did, okay, in the regular stoichiometry, when we were trying to figure out, we want to figure out which one of these two reactants is going to make more product. Right? So what we're going to do is we're going to find the ratio between these two, okay, and then we're going to find the ratio of the oxygen to the tetraphosphorus decoxide. Okay, so take a minute and find the number of moles that are created of our product. Let's find out our mole ratio, okay, when we're trying to figure out the number of phosphorus decoxide to just the phosphorus. So we have X moles of tetraphosphorus decoxide, okay, over 8.07 times 10 to the negative 3 moles of the phosphorus. We have 1 molecule of the tetraphosphorus decoxide over 1 molecule of the phosphorus. So we just transfer that over, okay, cross multiply, and we have X is equal to, well, because we have 1 over 1, it's just equal to 8.07 times 10 to the power of negative 3 moles of P4O10. Okay, so now let's find out the amount of oxygen. Okay, when we're using that many moles of oxygen, how many moles of the tetraphosphorus decoxide are we going to produce? Okay, so we have, again, X moles of tetraphosphorus decoxide over 0.432 moles of oxygen equals, we have 1 molecule over 5 molecules. So we're going to cross that over, and we're left with 0.432 times 1 over 5 molecules. So when we multiply those two together, 8.64 times 10 to the power of negative 2 moles. I put this in scientific notation. I put it in scientific notation. Now, which one is the bigger number?
The oxygen.
The oxygen, or the oxygen is the bigger number. Okay. The oxygen is the bigger number. So, which one is the limiting reactant? The phosphorus is the limiting reactant. So now it says, what mass of P4O10 is actually produced?
The atom.
Right? Well, what do you do now?
Oh, really?
Which one of the moles are we going to use? Right? Because now we're producing this many moles. We're producing this many moles or this many moles. Okay? So we know that the phosphorus is the limiting. Okay? Phosphorus is the limiting. But the question didn't ask us for that. But we do need to know that. Okay? We do need to know that because we've got, which mole are we going to use?
The phosphorus.
The one of? Phosphorus. Because when that runs out,
It's done.
it's done. Right? When that one's done, okay, it runs out, it's done. So we're going to use that. Okay, so we have that many moles. Right? We have that many moles. So what are we going to do to find the mass? What do we need to find?
Molar? No.
The molar mass. Molar mass of?
The totals. Yeah.
The tetraphosphorus decoxide. Take a moment.
Oh my God.
we know we're using this amount here, the 8.07, right? Because that's the one that we produce the least amount. So that is the number of moles, okay? The least number of moles we can produce with these two reactants. Now, we've got the number of moles. We need to find the molar mass of the P4O10. What's the molar mass?
2.29. That's what I got.
No, molar mass.
Oh,
283.9, okay? And it's grams per mole. So what relationship do we have according to our... We're multiplying. So we're going to take this number here, the number of moles, the lower of the 2 moles, and we're going to multiply it by the molar mass of our product, and we're going to get 2.29.
2.29. I got different because I used 284.
2.29 grams of tetraphosphorus decaoxide.